Okay, that's it. So we are on. Welcome everybody again to this session on elliptic curves. And today, actually, you'll start, Rakvi will start introducing you to this wonderful mathematical objects. So without further ado, Rakvi, the floor is yours. And to everyone, enjoy your session.
Okay, fantastic. So let me just start by mentioning what we already know. So for this talk, let K be a field, and we already know what field means. So keep both kind of examples in mind, like also infinite fields and finite fields. So like characteristic zero, for example, rational, real, or complex numbers. And also we have seen what finite fields are and what they look like. So both kind of examples are really helpful. So let me start by talking about projective coordinates, because our elliptic curves are, so it's a curve, right? So it's given by an equation, and the variables sort of sit in this projective space. So let me begin by talking about this. So in particular, I want to talk about P2 of K. So what it means is, like, I take tuple of three elements where A, B, and C, they are in my field, and I also want this not equal to 0. So I want at least one coordinate to be non-zero, and then I make an identification. And what is this identification? So two of these things are equal for me if and only if they differ by a scalar. What I mean is that this tuple is a multiple of this, where lambda is a non-zero scalar. It's an element of my field. Okay. Um, just a quick remark here. Like this type of construction, obviously there is nothing special about 2 here. So first remark is that this 2 can be replaced by any natural number. So in particular 3, 4, like in general n. So if we talk about Pn of k, then it's like when I talk of P2k, I take this set of 3 tuples. So when I talk about Pn of k, I'll take the set of n plus 1 tuples, and then I'll make the similar identification. Two of them are same if they are multiple of each other, but like this. The second thing is, in some general settings, instead of just insisting that we have a common lambda, we can instead talk about weighted projective space. By weighted projective space, I mean that instead of insisting that A2 is lambda times A1, I can insist that it is lambda times A1, where A is some constant. B2 is lambda B times B1, and C2 is lambda C times C1, where A, B, and C need not be equal to each other. They can differ from each other. In this case, we have that all of them are same, right? But as far as elliptic curves are concerned, we don't really care about this weighted projective space. But this kind of weightage becomes important when we talk about hyperelliptic curves. But we can talk about this more in detail if we ever discuss hyperelliptic curves or in that class. So some observations about this P2 of K. So its elements are now this thing under some identification, of course. So A, B, C, this is a condition, and then these elements lie in my field. And obviously, I'm making some kind of identification. So let me use so let me take an element A, B, C, right? So there are two. Let's say we choose an element in this set, in this projective space. So now there are two possibilities, right? First possibility is that C is non-zero, and the second possibility is that C is zero. If C is non-zero, then I can identify this A comma B comma C with A over C, B over C, and then 1. And now under this identification, you can actually think of this as, instead of projective space, you can just think of this as really affine space. So let me just write down the names just in case for future reference, or for sake of completion rather. Projective space, and when I say A to K, I mean affine space. And affine space is basically, it's the usual Cartesian product thing. So I just take this set of two tuples where X and Y both are in K, no restrictions. Okay. If C is 0, then my tuple simply becomes A comma B, and I can instead identify this with, so this is just A comma B, and you can identify sort of this with a copy of P1 sitting here, P1 of K. Because now I don't have to consider the third coordinate, right? I'm just down to two coordinates. So P2 of K can be thought of as union of two things, a copy of affine and this copy of P1 sitting in there. And there is nothing special about 2 here. In general, we would have, so if we take Pn of K, by the same sort of argument that we just did, instead of 3, we would do that for n plus 1. So we would have that it's a union of an affine copy and then a copy of Pn minus 1 sort of sitting there. Okay. So this is just sort of some basics about projective coordinates, and I just wanted to discuss it because we will use this terminology when we discuss elliptic curves. So let's get down to elliptic curves. So again, K is my field. Let me also assume further that characteristic of K is not equal to 2 or 3. And this is just a quick pop question. How do we define characteristic of K? Pop question, pop quiz, anyway. Okay, if I see no responses. So let me just recall what do we mean by characteristic. So remember, so this is just an aside. Recall. Let me write down recall. So in any field, we have two identities always, right? Additive identity and multiplicative identity. Or in simple terms, let's just call them 0 and 1, right? So characteristic of any field is the smallest positive number. And by number, I mean like a counting number, like a natural number. N such that when you add this multiplicative identity to itself n number of times, you get back 0. And this doesn't happen for any smaller n, right? So we have seen examples of both characteristic 0 and finite. So characteristic 0 would be something like a rational number where you keep adding 1 to itself and you never get 0, right? So this sort of a situation is called characteristic 0 situation. We also saw finite fields where we have prime characteristic. So that's what I mean when I say that for what I'm going to describe next, let's just assume that characteristic is neither 2 or 3. In other words, I am avoiding F2, F3, and their extensions. Okay. Or like polynomial fields with coefficients in F2, F3, and beyond. So, okay. So this is how I'm going to define an elliptic curve. Let's just give it a name. E is given by, and just for just so that we are clear about where these things are sitting, I think of this as sitting inside P2. So an elliptic curve is given by an equation of the form y square equal to x cube plus ax plus b. And these coefficients come from my field, right? Further, I want to insist that if we take all the roots of x cube plus ax plus b, now these roots, by roots I mean zeros of this cubic polynomial. Now there is no guarantee that these roots are defined over k. They can be defined over something else, right? Just to give an example, um, like for example, if we take simply x cube minus 1, right? Or let me take even a simpler example than that. Let's just say x square minus 2. This is a polynomial with coefficients in q, but the roots of this polynomial are square root of 2 and minus square root of 2, right? These roots are not defined over rationals, but they're defined over a bigger field, let's say real numbers in this case, right? So similarly, I'm talking about roots of this. So the roots need not be defined over k, they'll be sitting in complex numbers. So think of them as complex numbers. Or like a bigger field if you're talking about finite field. So that x cube plus ax plus b has distinct roots. So this is my definition. Okay. I'll call an elliptic curve of this form, sorry, an equation of this form an elliptic curve, provided the roots of my cubic polynomial are distinct. Now, just a technical thing, and please let me know if you want to discuss this in detail. I can discuss that, but I thought like for first introduction, I want to introduce like minimal equations. So like minimal equation in the sense I don't want to expose you to too many equations at one point. So what happens is, like, this is not, if you go to any textbook, this is not how elliptic curves are defined. So what happens is, like, this is speaking like in a very technical term, but Elliptic curves are basically non-singular projective curves of genus 1. And if you assume Riemann rock, then you can write an equation where you have many coefficients. So not just so you, like for example, you will also have y square plus something times y plus constant, and x cube plus something times x square plus something times x, and so on. Okay, so there are many coefficients. But what is nice is, like, if your characteristic of the field is not 2 or 3, then we can make change of coordinates such that we get this simple form, y square equal to x cube plus x plus b. Over characteristic 2 and 3, we do get this equation, but there are also other equations possible. Okay, so this is not the only case for characteristic 2 and 3. But we will, yeah, I will discuss some examples of characteristic 2 in next lecture. But for today, let's just assume that we are outside 2 or 3. So let's see some examples. Uh, so this was, yeah, this was example of polynomial. Let's see some examples of elliptic curves. So if we take y square equal to x cube minus x and think of them over R. So if you look into this polynomial, why 2 and 3 are not higher options? Yeah, that's what I was trying to explain. So what I was saying just a couple of minutes before was the actual definition of elliptic curve is that it's a non-singular projective curve of genus 1. Now, if you just work with that definition, then using Riemann rock, you can actually show that that's equivalent to writing down an equation. But that equation is not in this simple form that we are seeing here. There are more coefficients than that. Characteristic 2 or 3, when we are not in characteristic 2 or 3, we can make change of variables such that we get this simple form. Okay. In characteristic 2 and 3, some more, yeah, some more assumptions need to be made, so that you do get something extra apart from this. But yeah, that's why characteristic 2 and 3. Did I answer your question, or were you asking something else? Okay. Okay. So x cube minus x, right? This is an elliptic curve because if we try to take solutions of x cube minus x, so we can factorize this. This is x times x square minus 1, which again factorizes as x times x minus 1 times x plus 1. And the roots are 0, 1, and minus 1, which are distinct, right? So this is an elliptic curve. Second example would be y square equal to x cube plus, let's just say, let me use the one from textbook because I don't want to mess up with the pictures that I want to show. So this one, right? X cube plus x over 4 plus 5 over 4. I don't want to compute the roots right now because it's not easy to do it by hand, but you can check that they're distinct. Picture wise, if you want to draw a picture, for first one, it looks something like this. So, like there is an oval, and then for E2, something different happens. It's now, this is what I call the affine part of elliptic curve, right? Because these curves are not really sitting in R2 or K2, for example. They are really sitting in projective space. What we see here is just the affine part. So the picture that we see here is really the affine part. If we want to take projective coordinates, then what do we get? So let's go back to our equation. It's y square equal to x cube plus ax plus b. So affine part, right? So I'm making this assumption essentially that xyz is, there is this sort of identification uh, going in the background. So this y that we see is really y over z. So let me write down that this is x cube over z cube plus ax over z plus b. Now let me try to simplify this. So y square over z square equal to z cube x cube plus ax z square plus b z cube. And now if I want to cancel z's from the denominator, I'll get zy square equal to x cube plus ax z square plus bz. Now when I say what we were discussing before is really the affine part, by what I mean is if we just substitute z equal to 1, we will get back what we started with. But this is really the projective part, right? So now as we saw for projective space, there is the affine part and then there is the projective part where last coordinate is 0, or in this case z would be 0. So let's just try to see what happens if z is 0. What kind of points do we get on our elliptic curve? So if z is 0, so we get 0 equal to x cube plus everything else is 0, right? So that tells us that x is 0. So we have x 0, and then there is no condition on y, right? So y can be anything, and then z is simply 0. This can be identified, like any such point of this form can be identified with 0 1 0. Because remember, y cannot be 0 because I want at least one coordinate to be non-zero, right? So all these points can be identified simply with 0 1 0. So this has a name. This is called point at infinity. Also, in some textbook, it's pretty common to use like a fancy O for this. Like not this O, sorry. Like more like if you go to LaTeX, I think that's I don't know, that's a script of frac or something. I think frac would give a correct thing. So like some sort of a fancy O. Uh but I'm not very good at typesetting what LaTeX can do, so I'll just simply call it we will denote it by simply infinity. So there is always this special point that we have. And this is like obviously it's not able, like it's not possible to draw it on the paper because paper can only show the affine part. This is really the projective part. Let me take a moment to acknowledge why do we care so much about these projective spaces. A priori it looks like when we see definition for the first time it looks slightly convoluted and complex than the affine part, because affine is easy to define, right? You just take set of two or three tuples and that's it. But here we are taking like some tuples and we are making some identification. We don't know why do we do that. The thing is, geometry becomes simpler over projective spaces because there is this famous. So this is nice side. Why do we care about projective spaces? So a quick answer is that geometry is simpler over projective spaces. Because to take a very basic example, let's take an example of two lines, right? If we just restrict ourselves to affine space or just say R2, right? So let's take um example of two lines. So think of line as sitting in the usual Cartesian space or R2. So we know that in affine space, there are three conditions possible. So the lines can be parallel to each other, or they intersect at a single point, or uh, they are really parallel, but like a double line sort of a situation. But let's just avoid it. Okay, it's really not interesting. But yeah, so either there is unique solution or no solution. But this sort of thing won't happen for projective spaces, because if we are willing to imagine these lines in projective spaces, these two will meet at infinity. So in projective space, lines meet at infinity. These lines. So the case of empty solution doesn't really exist. Or the famous Bezos theorem that a curve of degree m, we just saw an example of line. Line is really a curve of degree 1, right? A curve of degree m and a curve of degree n intersect at m times n points. These kind of results are hard to state over affine, because we can very well have, like we just saw, right? We can possibly have no intersection. But over projective spaces, we also have we always have solution. So this is things become slightly simpler than that. So just wanted to give a quick motivation. So anyway, let's go back to elliptic curves. So going back to elliptic curves, we have this affine part, and then we always have our point at infinity, which will always be part of the picture, right? But we are done with that, because we know in the infinity part, so to say, there is only one solution. So we can just focus on this: y square equal to x cube plus x plus. Now, what is really remarkable about elliptic curves and why they are so interesting and fascinating is that we can add 2 points on elliptic curves, which I still to the date find very fascinating. Because if you just give me an abstract or a random curve and you ask me to add 2 points on it, I don't even know how to do that or how to make sense of that thing. But these curves, they have some fascinating geometry going on for them. And how does this addition work? So let me try to explain it visually, and then we will see how to write down equations for it. So going back to our figure, let's say our elliptic curve looks something like this. And let's say I take 2 points on it. Let me use a different color. So let's say I take this point P. Let me call its coordinate x1 and y1. And let's say I have another point Q. Sorry. Let's say its coordinates are x2 and y2. So how do I add these 2 points? What do I do? Well, first step is I take the line joining them. Okay. Now a line, as we just saw, is a curve of degree 1. And my elliptic curve is really given by the cubic equation. So it's a curve of degree 3. And my Bezos theorem tells me that they must intersect at 3 points, right? I already have two. So there must be a third point that it intersects into my curve, right? So I'll take that third point of intersection and I'll give it a name also. I'll call that R. The coordinates are something x3, y3, let's say. Now what I do is I take reflection of this. So when we take reflection like this across the x-axis, we know what the coordinates are. The coordinates will simply be, so x won't get affected, but y will become negative. This is my point P plus Q. This rule has a name. This is called chord law or chord law of addition. Basically, what I'm doing is like we are taking chord joining two elements and then we are trying to intersect it in the curve to get the third point, and then we reflect it across the x-axis. If P was equal to Q, let's say, then how do we do this? Because we don't have a chord anymore. So let me open a new page. If P is equal to Q and P is not equal to minus Q, because if P is simply equal to minus Q, then basically P, if you want to add these two things, like let's look at this, like basically P plus Q is minus R here, right? If you want to add R and minus R, and if you take the chord joining them, it will be a vertical line. And where will this meet the curve? This will meet the curve at infinity. And if we take reflection of infinity, we get back infinity itself because that's the only point, right? So if P is minus Q, P plus minus P is simply the point at infinity, right? So that is okay. Suppose I'm not in that setting. I want to add P to itself, assuming that, yeah, that P is not its own inverse. So let me draw that picture again. So this was my P. For picture's sake, let me just use a better point. Let me just place my point here because I want to draw nice pictures. So let's say this is my point and I want to add P to itself. So what I do is, now I don't have a chord, but I do have a tangent. Okay. So I'll take this tangent instead. Now we can think of tangent already has like these 2 points, right? So I can still I can still find the third point where it intersects. Let me call it R. And now the same thing. I take its reflection and that is my 2P. Take its reflection and this point is 2P. So the only difference is instead of chord now we have tangents. Okay. Let's just see how do we, so this is a visual representation. Okay. But some things that we can, why take the reflection upon the x-axis? That's a very good question. It's a very natural question. See, the thing is, if we don't take reflection, we don't have, because if we don't take reflection, we can't think of these points as group. Only when we take the reflection, it makes sense to talk about these points as groups. So whatever addition I have described, so with respect to this addition, the set of all k points of my elliptic curve is a group. And let's just recall groups here, because I think we discussed this in lecture 2, which was 2 weeks ago. So what is a group? Group is a set along with a binary operation. So in this case, my set is set of k points of E. And by binary operation, I mean a rule of combining two elements such that the element that I get as an output is again member of my set, right? So in this case, the binary operation is addition, right? And what do I want? I want this addition to be associative. I want to have an identity. I want to have inverses. And yeah, but this is all we need for a group basically. So checking that this procedure is associative is hard to do it just by looking at the pictures, right? Because a priori it's not clear that if I take 3 points, let's say p1, p2, p3, then the order of addition or the parentheses don't really matter, right? It's not a priori clear. But it can be verified once we see the equations and we write down equations, okay? So associativity can be checked by equations, not really visually. Identity is easy to check. So let's see. Do we have a guess for identity? What can be, yeah, what should be the element that constitutes as infinite? Sorry, as identity. Infinity. Yes. So the point at infinity is our identity. And inverses, we just saw. Like if you just take reflection across the x-axis, that's our inverse. So inverses do exist. Let me just write down they exist. What is further true for this set or this group? So this already verifies that it's a group, right? But what is further true is that this operation is also commutative. And this can be verified visually very easily, right? Like how I just defined p plus q is same as q plus p, right? Because I'm just taking the chord joining them. So ultimately that whole operation it does not depend on the order of p or q. So this is also commutative. So this set is an abelian group. And there is this nice theorem that follows from. Okay, let me just write down the theorem and then we can talk about it. So this set of points E of k is not just an abelian group, it's actually a finitely generated abelian group. And so what can we say is that we can break this into two parts. We can break this into two parts. There is a free part, and then there is something called the torsion part. I'm not explaining a lot of notation here. Like for example, this plus inside the circle. By that I mean direct sum. Think of it as really like a Cartesian product. Okay, so I'm not explaining a lot of things here, but I just wanted to introduce something. So this R that comes from free part is basically what is called rank of this elliptic curve. And then there is this whole torsion part, right? And this rank is very mysterious. So you might have heard about BSD conjecture that says that this rank is actually related to L function of an elliptic curve. And if you give me any random elliptic curve, then computing its rank is hard. In fact, proving heuristics that, like, let's say, what can we say about the average rank? Is it half? Is it so? Like even proving these kind of things are really hard. And some work has been done in this direction, but let me just say that this rank part is really mysterious. Okay, but yeah, this theorem is not really necessary for what we are going to discuss. I just wanted to give a glimpse of where does rank come from. Anyway, so this set is an abelian group. We have not yet checked that it's associative, but we can once we see the equations. So let's just see some explicit equations. Okay, so explicit equations for addition. So let's say our curve is x cube plus ax plus b, and I want to add 2 points x1, y1, and x2, y2. So what do I do? First of all, I take the line joining them, right? And what is the equation of line joining 2 points? If you remember the point slope formula, it's so let L be the line joining P and Q. So what is L? The equation for L, if we take the point slope formula, it's given by y minus y1 equal to y2 minus y1 times x minus x1. Okay, this is my line. Let me use a shorthand notation for this slope because this kind of fraction, like it's kind of hard to write. So let's just say that, let me call this m, small m. Okay. So my equation is y is equal to m times x minus x1 plus y1. Now I want to intersect this line with my curve, and I want to find that point of intersection. So what will I do? I'll plug in. So let me call this equation number 2. My first elliptic curve is equation number 1, right? So plug in 2 into 1. So plug in value of y into 1, right? So what do I get? So we square it. So we'll have m square x minus x1 square plus y1 square plus 2 times m times x minus x1 y1 equal to x cube plus ax plus b. Right? This is my equation. It's purely given in x. And so I already know two roots for this, right? X1 and x2. I want to find out the third point of intersection. So I want to find out the third root of this. So a quick recap about polynomials, how polynomials work. So if we take coefficient of x, sorry, not x, x square. Yeah, x square. So coefficient of x square is basically negative of sum of roots, right? And constant coefficient is negative of product of roots. So so let's just take in this equation. Let me call this 3. Let's find out coefficient of x square in 3, because that will give me the third root, because I already know 2, right? X1 and x2. So what is coefficient of x square? Well, I have m square. So if I open the brackets, I'll get m square times x square. So I definitely have x square and then nothing else. And then, yeah, the 2 times m times x minus x1 times y1 doesn't give me x square. And I have nothing on the other side also. So the coefficient of x square is simply m square, right? But this is on the left hand side, right? I will bring it into RHS. So the coefficient will actually be negative of m square. So this coefficient is equal to negative of sum of roots. So the roots are x1, x2, and let me call the third root x3. Okay. So that gives me, so that tells me that x3 is simply m square minus x1 minus x2. And our m was nothing but the slope. So this is y2 minus y1 over x2 minus x1 square minus x1 minus x2. This is the x coordinate of my p plus q. Because remember, even after taking, let me just go back to the picture. So even after taking reflection, the x coordinate doesn't change, right? So the x coordinate is basically the third point of intersection. Now I just want to find y3 and take its negative. That will be the y coordinate of p plus q. So y3 is, so remember how do we get y from x? So I use equation 2. Okay. I use equation 2. So using equation 2, y3 is so m times x3 minus x1 plus y1. So m times x3 minus x1 plus y1. But I don't just want y3, I want negative, right? Because we are taking reflection. So negative of y3 is m times x1 minus x3 minus y1. So p plus q, the coordinates are x3 and minus y3. But this is the formula. So I know my x1, so I know the points that I'm starting with, right? x1, y1, x2, y2. So using that, using this formula, I can compute x3. And once I know x3, I compute y3. And this is my equations of addition. Okay. Let me just pause here for a second. Any questions? No? Okay. So let's just move ahead. And while we are at it, let's also see equations for point doubling. Like if q is equal to p and p is not equal to minus q, then what do we get? So now I don't have so equations for 2p. So let's go back to our picture. So now we don't have chord anymore, but instead we have tangent, right? And to write down equation of a line, I need slope and an intercept. Well, intercept is given by this coordinate. I need slope. So let me just ask this question. How do we calculate slope of tangent? If anybody knows the answer, otherwise it's okay. I mean, we will see how do we compute it. But yeah. So we take the derivative. Okay. So if we are given a curve and we have a point, and at that point we draw a tangent, and we want to compute the slope of the tangent, we simply take derivative of the equation at that point. Okay, so we need to take derivative. So to find out slope of tangent, we need to take derivative. So we have to go back to equation of elliptic curve, right? Our equation was y square equal to x cube plus ax plus b. So if we take derivative on both the sides, what do we get? So derivative of y square is 2 times y. And since y is a function of x, we are really thinking of x as a free variable and y is the dependent one. So sort of chain rule. So it is y dash. And now derivative of right hand side is 3x square plus a. Alright. So y dash or dy by dx is really our slope that I'll again call as m. And this is 3x square plus a over 2y. So now same thing. Um, what we did, we can do the same thing again. We have the slope, right? So we can write down our equation of the line. We can intersect. We can again look at the coefficient of x square. And but it's essentially the same analysis. So the x coordinate for 2p will be given by slope squared. So 3x square plus a over 2y square minus 2x1. And y coordinate will be given by 3x square. Oh, 3x. So slope at x1, y1. So 3x1, y1. Yeah, sorry. And y coordinate will be given by 3x1 square plus a 2y1 multiplied with x1 minus, let me call this x2p and y2p. Just to denote that we are talking about x coordinates of this 2p. X1 minus x2p minus y1. So this is how we really double the point, right? It's basically the same calculation, just the slope has changed. And how do we get the slope? We get it by taking derivative. All right. Um, so in the remaining segment of this course, I think we have about, because we started late, so I think we have about 10 to 11 minutes. Let's just take a very explicit example of an elliptic curve, try to compute its points, and then let's try to add 2 points and see what we get. Okay, just to get some hands-on example. So let me take this elliptic curve. So this, let me just give some explicit calculations. So let's take this elliptic curve given by y square equal to x cube plus 4x plus 6. And the field that I have in mind is now the finite field of 7 elements. Okay, this is an elliptic curve. Yeah. So what are all the points of this? So E of f7, I want to compute this set. So obviously we always have infinity, right? So let's just write that down in the beginning. And now we are down to affine part, right? So what is the strategy? Well, we are now in f7, right? So x and y both take values in f7, and we know f7, it's a finite set with only 7 elements. So what I'll do is I'll try to plug in values of x and see if I get a solution for y or not. But before that, since like we have y square in the end, right? We have y square on left hand side. So it's important to know what are the squares. So squares in f7. So if x is 0, x square is 0. If x is 1, x square is 1. If x is 2, x square is 4. If x is 3, x square is 9, but 9 is really 2 in f7. And now 4 onwards, because 4, 5, and 6. So 4 is basically minus 3, right? And negative doesn't have an effect on squaring. So square of 4 is also 2, 5 is 4, and 6 is just 1. So the squares are 0, 1, 2, 4, right? So now let me just try to find all the points. So if I plug in x equal to 1, I will get y square equal to 1 plus 4 plus 6, which is basically 11 but 11 is 4 in F7. So y square is equal to 4. That gives me two possibilities for y. So looking at this table, I get 2 and 5, right? So I have 2 points, 1 comma 2 and 1 comma 5. So similarly, we can do this. We can do this calculation for every possible value of x and see what y coordinates we get. For example, if we do this for x equal to 3, then we'll get that y square is equal to 3 cubed, which is 27, plus 4 times 3, which is 12, plus 6. So I get 33 plus 12, which is 45. And this is 3 in F7, right? But I never get 3 as a square. I never get 3 as a square. So there is no solution corresponding to x equal to 3, right? So I can do this, and all the solutions that I get are so 2 comma 1, 2 comma 6, 4 comma 3, 4 comma 4, 5 comma 2, 5 comma 5, 6 comma 1, and 6 comma 6. So we can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points. Further, if we just take 2 points and if we want to add them explicitly, so for example, let's just say if we want to add 2 comma 1 and 4 comma 3, then using the equations that we had before, like we compute slope and everything. So if we do all that calculation, we will end up getting 2 comma 6, which is again a point in my set, right? And if I want to double, let's say I want to add 2 comma 1 to itself, I'll get 4 comma 4, which is again an element in my set, right? So this is just some explicit calculation. And also the fact that so just some quick observations here. The fact that the size of my group is 11, it really tells me that E of F7 is cyclic. By cyclic, I mean it is generated by a single element, simply because its order is prime, right? So this is a more, like, this follows more from a general observation. So let me say more like a proposition, which can be very handy while doing some uh, like explicit calculations. So let G be a group. Let G be a finite group. By finite group, I simply mean that as a set, its cardinality is finite. So if order of G is prime, then G is cyclic. And by cyclic, I simply mean that it is generated by a single element. Or uh, by generated, I simply mean that you take an element and you keep applying operations to itself and you will generate the entire group. Okay. And this can be proved by observing this, that choose any element G in G such that G is not equal to identity. And we take the subgroup generated by G. So we take G and then we multiply G with itself or compose or apply the operation. So G square, G cube, G4. Keep on doing that. This sits inside Z, right? This is actually a subgroup, right? An order of a subgroup has to divide. So order of this subgroup has to divide order of G. But G is really a prime number. So order of G is really a prime number, right? And what are the divisors of prime number? It's one or itself. So this group is clearly not one, because I'm not taking an identity element, I'm taking a non-identity element, right? So that tells me that order of this group has to be order of full thing. So if we have a subset whose size is equal to the set itself, that means that these are really same. Okay. So yeah. So in other words, E of F7 is generated by a single element. Or in other words, if you take any element here apart from infinity and you just keep adding that point to itself, you will recover the entire group. So we can take 1 comma 2 for example. So add 1 comma 2 to itself, you will get another point. Then add 1 comma 2 three times, you will get back. So ultimately like this, we will recover this entire group. So that's what I mean. And yeah, let me end here, because I think I only have 2 minutes and I cannot discuss anything else. So let me just end here and we'll continue from here on next week. Yeah. Okay. Uh, yeah, if we have any questions, we can take that. Is it not natural to define multiplication and or division of points based on I didn't get your question. Is it not natural to define multiplication of points? Okay, we already have something called addition of points on elliptic curves, right? So you're talking about defining a new operation called multiplication, and you want to do that but this is just like addition, right? You're basically adding p to itself. Sorry, we are basically adding m to itself p number of times, and you want to call it p times m. Yeah, you can do that. I mean, I guess the question is this a valid terminology? Yeah, of course, you can use this. Like when I say, like for example, 3p, what I mean is p plus p plus p. So yeah, this is a valid terminology. By valid terminology, I mean I really mean like you see this in textbooks. So yes. I wouldn't use the word multiplication for it, because it is essentially addition at the end of the day. So we have a group operation and we are just doing that. So
Okay, is that me? So do we have any other? Thank you, Rakvi, for the session.
yeah,
Maybe I'll stop recording for people to feel more comfortable. Those attending now to ask any questions.
sure. Yeah. Yeah, I specifically want to ask this. So if there is an interest about discussing more of this, like more theory in this, like what I talked about in the beginning, like elliptic curves are basically non-singular projective curves of genus 1. And how do we get this equation? Is essentially using Riemann rock. Okay, so if we want to see Riemann rock in detail, or like in, yeah, let me know. Essentially, yeah, we can do that.
Yeah, you can. I think that's a good point you made, Rakvi. This is why we encourage you to join the Zulip channel. You can ping Rakvi there if you want to go in more details with this. The notions that she covered.
I think it would be good to touch on Riemann rock a bit more.
Okay, let's do that next week then.
Thank you, Rakvi.
Okay.
Yeah.
Yeah, I will stop recording, and then anyone else who wants to do any interview.